In this video, we are interested in linear regression in very high dimensional spaces, and we look at a proposed low complexity approach which we call coded compressed sensing. Mathematically, we get observation vector y, which is equal to matrix A times vector S plus some noise. We know that S is sparse with k non-zero entries, and A is a very wide matrix with possibly on the order of 2 to the 128 columns. The performance evaluation we're interested in is the number of mistakes in the support recovery task normalized by the number of non-zero entry, k. This criterion is related to the per-user probability of error, which was defined in the unsourced MAC problem. And the performance target is on the order of 1 through 5%. An important point in viewing this problem as a compressed sensing problem is to realize that we have complete control over the sensing matrix A, and we can also embed some structure in our vector S. A concept that provides a foundation for coded compressed sensing is the multiple perspective of a message. So we view a message as a sequence of bits, and sometimes we also view it as the integer value that corresponds to reading these bits on a radix 2. And a third representation is the index vector, which is a vector of all zeros except for 1 in the particular location of the integer value of the message. The conceptual progression then goes from a sequence of bits to an integer to an index vector, and the index vector determines the signal that will be transmitted on the channel. So when we have multiple devices, we've seen this representation before, we have a number of messages that are the blue dots. Through matrix multiplication, these dots will determine the sum of the signals that get sent on the channel. In other words, they select the columns of A that get added and become the observation with some additive noise. One of the challenges with this compressed sensing problem is that the size of the matrix is huge. With 2 to the 128 column, it is not amenable to using standard off-the-shelf compressed sensing solvers. A possible approach is to use a divide and conquer strategy to send messages. And what we mean by that is we start with a binary message, and then we partition it into blocks of a size, say 2 to the 16, that we can manage with standard compressed sensing solvers. And then the different devices then send these blocks in different rounds of compressed sensing. So in the first slot, all the devices send their first 16 bits. In the second slot, all the devices use their second set of 16 bits, and so on. And then within each slot, we perform a compressed sensing solution to the problem and recover a list of the fragments that were sent. Of course, one issue with this approach is that for every slot, we only recover a list, but we're not told how to put the messages back together from their fragments. To overcome this issue, we turn to forward error correction. And in particular, we add redundancy to the message before partitioning it into blocks. So here at the top, we have the information message in bits. The next step is to add redundancy in the form of an error correcting code. And then the blocks are transmitted through suitable sized compressed sensing problems. The redundancy that's added to each block can subsequently be used to stitch the pieces of the same message together using error correction. When we put this problem together, what we have is the message that's being sent collectively contains, say, W bits and P parity bits in a structured fashion. The encoded message is partitioned into blocks of a suitable size. From a device perspective, each of these blocks is sent in a different slot. So we have a collection of L compressed sensing problems of a manageable size, and each device sends a one sparse vector over a slot. The multiple access channel then brings these messages together, and the receiver gets the sum of all these messages plus noise. From a channel output perspective, what we get is in slot 1, we have k devices, each transmitting a one sparse vector, and we perform a compressed sensing task, and we cover the list of all the fragments. From the slot 2, we get the same compressed sensing problem with K1 sparse messages that are added up by the channel and recovered at the receiver, and so on for slot 3, 4, all the way up to the last slot, which we label slot L. So altogether, we have L instances of CS problems, and each can be solved using a standard compressed sensing solver. Here we can either use the non-negative least square compressed sensing solver, or we could also possibly turn to an approximate message passing based recovery scheme. This produces L lists, each of K-decoded subblocks with parity. So here they're shown in white, with the parity bits are appearing in blue. And the subsequent task for the decoder is to piece together the fragments that belong to the same message. And for that, we introduce a tree code and a tree decoder. What we want is, starting from a root fragment that's on list 1, we want to be able to go forward in a low complexity fashion and find the fragments that are associated with this root block. Here we have selected the second item on list 1 as our root fragment, and then we would like the ability to stitch it using the parities to be able to recover the second block, the third block, all the way down to the final block of the original message that was transmitted by a device. We know from coding theory that random parity check bits are very effective in certain contexts. So we designed a tree code that's based on adding random linear combination of the information bits that precedes the parities. Every parity bit is a linear combination of the information bits that precedes it. Pushing parity bits towards the end improves performance, but it comes at the expense of complexity, whereas early parity bits enable the rapid pruning of the tree at the expense of performance. Conceptually, the decoder starts from a root fragment. It considers all the blocks on the second list and checks whether their parity pattern matches the parity pattern generated by the first fragment. The blocks that do not match the parity pattern are discarded immediately, whereas the other block are retained for further analysis. The tree decoder then descends to the next level, computes the parity pattern for all the valid paths, and looks at the lists for the third slot and retains the code words that are consistent with the parity patterns that were computed. This process moves forward until the last list is reached and the original message is recovered. To know where to place the parity bits, we need to understand the pruning process a little better. And our starting point is a classic code word with some parity bits. So consider a code word with, say, 2 information bits and p parity bits. The code word is produced by systematically encoding the information bit using a random parity matrix G. So the parity bits then become p equal to w times g. If the bits in the random generator matrix G are chosen from 0, 1 at random with equal probability, then we can compute the probability that a random code word fulfills a particular parity pattern. So the probability that a randomly selected information vector WR produces the same parity pattern as a subcomponent is simply 1 over 2 to the rank of the generator matrix. We should mention here that the parity pattern is computed using modulo 2 arithmetic. The proof is simple. The probability that parity pattern PR is equal to true parity pattern P has to do with the fact that the randomly selected information vector WR times the generator matrix G should be equal to the true information vector W times the same G. This is equivalent to the modulo 2 sum of W plus WR being in the null space of G. Since the null space of G plus the rank of G is equal to the dimension of W, and since the probability of picking a random WR is 1 over the dimension of W, then we recover the result of the lemma. The analysis gets slightly more complicated when you have several fragments. So here our vector is composed of information fragment W1, and then the second block is composed of information fragment W2 and parity fragment P2. The third block is also composed of information bits plus parity, and so on. The parity P2 are based on the information segment W1. Parities P3 are based on information segments W1 and W2. And finally, parity pattern P4 is based on the information segments contained in SUT 1, 2, and 3. Consider an alternate vector whose segments are taken from different devices. So here we have the first segment, W1, is coming from device I1. The second block is coming from device I2, and so on. We want to reflect on what is needed for this vector to survive the parity check constraints. To survive the first round of the parity check, the parities in the second block have to match what would be generated by the first block. So in particular, Wi11 times G12 has to be equal to Wi21 times G12. By linearity, we can express that as Wi11 minus Wi21 times the generator matrix 1, 2 should be equal to 0. For this candidate vector to survive the second parity check stage, or P3, what needs to happen is the parity that were generated by the true vector I3 should be equal to the parities generated by the information bits coming from Wi11 and Wi22. Like we did before, we can create an aggregate vector and make sure that its product times the generating blocks is equal to 0. In this case, this will be Wi11 minus Wi31 times G13 plus Wi22 minus Wi32 times block G23 should be equal to 0. For the next stage, we have something that's slightly more complicated, but has a very similar form. In this case, parity pattern P4 was created using information block Wi41, Wi42, Wi43 times the generator matrix, and the contending information blocks have to form the same pattern. So when you multiply Wi11, Wi22, Wi33 with generator blocks G14, G24, and G34, you should get P4 again. And we can summarize this equation using the last line. Conducting the same type of analysis that we had 2 slides ago, we get that the probability of a candidate vector whose blocks come from different devices will survive the parity check process with a probability that depends on the rank of the generator matrix. And in the current problem, the generator matrix is this block triangular matrix where the top component is G12, G13, G14, the second row is a 0 followed by G23, G24, and so on. One of the challenges with the analysis of the performance of the tree code comes from the fact that if an erroneous vector has blocks coming from different devices, but some of the blocks come from a same device, then the discrimination process coming from the parity bits is not as strong. On the last line, we show how some of the blocks of the generator matrix will essentially disappear for the purpose of discriminating erroneous code words when some of the fragments are coming from the same device. Let's see what happens through a simple illustrative example. Here the levels can be thought of as a labeling of the devices, and the candidate code word is formed by taking one block from every device. In SUT 1, the block comes from device 2, in SUT 2 it comes from device 1, in SUT 3 it comes from device 3, and in SUT 4 it comes from device 4. So levels are not repeated, and for this type of code word, the probability that the tree decoder detects this is an invalid code word is 2 raised to minus the rank of G, where the G is this block triangular matrix. The story is different when devices are repeated. And as an example, we consider the following pattern where during SUT 1, 2, and 4, the blocks are coming from device 1, and then during SUT 3, the block is coming from device 2. This is still an erroneous candidate, but in this case, levels are repeated. the probability that the tree decoder is able to identify this erroneous candidate is 2 to the minus the rank of G, except that entries in G have now disappeared because levels are repeated. In this case, we are left with 3 blocks, G13, G23, and G34. The rest are zeroed out. The exact analysis of the probability of error of erroneous candidate for the tree code is quite involved, and it relies on J patterns. These combinatorial objects grow quite rapidly, and so for long tree codes it becomes intractable to compute the exact probability of error. Consequently, we need an approximation of this quantity to be able to allocate parities at judicious blocks. As discussed before, the allocation of parity is a natural trade-off between the complexity of the problem and the expected performance. Since the exact analysis is too cumbersome for the tree code, we use the approximation where we assume that candidate code words are formed from blocks coming from different devices. In this case, tracking the expected number of erroneous paths who survive the parity check process is tractable. The notation we use is PL is the number of parity in subblock L, capital PL is the number of erroneous paths that survive stage L, and the complexity of the process is denoted by C sub 3. It turns out that the number of paths surviving stage L conditioned on the number of paths who survived at the previous stage under the approximation we mentioned is a binomial random variable. As such, the expected of paths surviving the process can be computed using nested conditional expectation. The steps are outlined on this slide, but the fact that you can carry this computation is more important than the exact answer at this point. The complexity of the process is roughly equal to the number of parity check equations that must be computed, and the expectation of this variable can also be computed. The placement of parities is an optimization problem that naturally trades off complexity and performance, and we pose it as a minimization of the expected complexity subject to the probability that an erroneous path survives the process being less than a certain quantity epsilon. The other constraints are that the total number of parity bits is fixed and the number of parity bits per subblock should be an integer. The relaxation comes from disregarding the integer constraint, and the resulting problem can be solved using a standard convex solver, such as the CVX library. On this slide, we show the nature of the parity allocation. The leftmost column represents the probability that an erroneous path survives the process. The middle column is the expected complexity, and the rightmost column is the optimal allocation for the parameters given. From top to bottom, the probability on the detection of erroneous code word is increasingly stringent, and in the middle column, complexity also increases. What I want to point your attention to is the character of the bit allocation, where the first few packets do not have many bits, and then it's followed by a constant bit allocation, and then at the end, parities allocated heavily to the last blocks. This leads to the following type of behavior where the tree of possibility is allowed to grow to a certain girth during the initial phase of the process, and then there's a maintenance phase of the girth where the number of parities per block is essentially constant, and at the end you have an aggressive phase where the tree is pruned down, making sure that with high probability only the valid code word survives. This slide shows that the performance of coded compressed sensing did very well compared to other schemes at the moment of its introduction. Since then, other schemes have been proposed for the UMAC, and they will appear later in the tutorial. We also want to point out that the ideas from tree code and coded compressed sensing have been used in other research. For instance, CheerUp is an algorithm tailored to the unsourced multiple access with very low complexity. It is based on the second-order Reed-Muller function, and to maintain the low complexity, it uses the Hadamard projection twice. As part of this scheme, the author used a tree code to stitch the different instances of the compressed sensing scheme together. A second area where ideas from tree code have been used is in unsourced random access with massive MIMO receivers. As a summary of coded compressed sensing, we have this notional diagram. At the top, we have the information message in bit. This information message is enhanced with parity, leading to an encoded message, which is partitioned into blocks. These blocks are translated from their binary representation into an index vector, and this index vector chooses the signal that the device transmits. The many devices transmit over the multiple access channel, leading to multiple instances of compressed sensing. The receiver decodes these compressed sensing instances, leading to lists of fragments. And as a last step, the tree decoder uses the parity pattern to stitch the fragments together, leading to the transmitted messages. And this concludes our overview of coded compressed sensing.